Let's keep talking about electrolysis and the electrolytic cell. In general, an electrolytic cell is when you apply an external source, it could be like a battery shown in this picture, to provoke a redox reaction that otherwise would not happen, or at least would not happen in the direction that this external source is able to do. So first, let's remember that in our previous video we were setting up that electroplating system in which you had that ring and you applied an external source so that this was silver and there was a flow of electrons from the anode to the cathode as usual, and that would create a pretty thick, as you can see on this picture, coat of that specific metal. Notice, however, that we have not mentioned that one has to be careful at applying voltages here, because what pretty much you're doing by applying a voltage is that you want to remove electrons from this part and put electrons in here. So you have to be careful in terms of, well, you do not exactly know what is the species, mostly when you have more than one compound in your solution, what is the species that will be oxidized and reduced. So the most simple case, I'm just saying, you could maybe, since this was water, and we will explain why that did not happen, but you could have oxidized water in this electrode. That did not happen because it was not the most favorable thing to happen, so we'll have to be careful when you have more than one compound in your electrolytic cell. But in the most simple of the electrolytic cells, what you have is just one single compound. So imagine that it'll have to be a very warm electrolytic cell because you have molten salt, molten sodium chloride liquid, and you add this external source, and this will be your anode because you decide that to be the anode. You apply an external source such that the electrons are removed. So the only thing that can be removed here will be the only species that you can oxidize would be the chloride. Notice that sodium plus is already way too oxidized. So you're not going to remove an electron from sodium plus because it already has noble gas configuration. And then if by applying the external potential you will reduce the sodium plus. So, and that's the most simple of the case when you have just a pure compound. If you have a solution with water and other ions, you have to be careful. If you have pure water, for example, your electrolytic cell, let me postpone this, your electrolytic cell will oxidize and reduce water. And notice, like the picture in here, you obtain twice as much hydrogen than oxygen, so most likely this is the hydrogen and this is the oxygen. And this is the whole idea, the whole meaning of the word electrolysis means exactly that, to break. You can break compounds apart. In this case, water would do nothing unless you apply an external source, so you can break water apart. So that's hydrolysis, if you will, hydrolysis. But in this case, because it's with an external source, is electrolysis. So when you have pure compounds, it's pretty straightforward to see what reaction is going to happen. The cations will reduce, the anions will oxidize, and you will have these compounds in here. Okay. So you're expected to know what is the product of electrolysis from a pure compound. You identify the cation, you identify the anion, you remove the electron from the anion, or if you will, the most electronegative, and you give the electron to the most electropositive, to the cation. Okay, so let's practice some, and this problem is very similar to the problem that we solved in our last video. It's applying again the Faraday's law, but just in this case we have a molten salt, and I would say the question is about identify the metal, so do not think that is sodium. It is not. But it's going to be, you have a molten salt, you apply an external source at a constant 3.86 amperes during 16.2 minutes, and you realize or count that you deposit 1.52 grams of metal. You're supposed to identify the metal. Alright, so let's try to solve this. We have the current going for 16.2 minutes, and because Amperes is defined as coulombs per second. We need to convert those minutes into seconds. So 1 minute is 60 seconds. And now I'm applying the coulombs per second. Coulombs per second. In 1 second, I have 3.86 coulombs. That's the very definition of amperes. Now, coulombs into mole of electrons, 96,485 coulombs. There is 1 mole of electrons, and now we would need to know the charge of the metal, but notice that it comes with chloride, therefore our metal has to be 1 plus. So there's only, the relationship is 1 to 1, 1 electron, 1 mole of electrons, 1 mole of metal. So let me just put it here, 1 mole of electrons, 1 mole of metal, and 1 mole of metal, the atomic weight of this metal that I do not know. But what I know is that I obtain 1.52 grams. Okay, so if one divides this whole combination, let me call it this X, so the atomic weight is 1.52 divided by all this number, and you will see that you obtain something around 39 grams per mole. This is potassium. Therefore, the salt that you were doing the electrolysis was molten potassium chloride. Better know what you have in your molten salt. You never know what reactivity you may have. This would be a very high temperature, of course, because this is at room temperature, is a solid. In this case, it's a liquid.